Hi guys, I'm Kyungmin Kim, and I'm a graduate student majoring in Industrial Management and Engineering in Pohang, Korea. Today I'm here to introduce the intuition of what the principal component is. So let's think of a design matrix. As usual, statistical settings of size and by P. And we've got to center each column vectors of variables. So if we express the matrix of M by P like this, if we center each column vectors using the projection matrix, we can describe it as follows. So let's say X tilde is a uncentered a matrix with uncentered columns, and let's define X as this way using the projection matrix onto the constant. Onto the constant vector. So if you see this, you'll see that the second term can be expressed in terms of the outer product. Here 1 refers to a vector of length n, not a scalar. So like this. So I put t here in order to show that it is a row vector. So it is a outer product. So, yep, the X matrix is a matrix with centered columns. Yep. And if we take the X transpose X and divided by n or n minus 1, either is okay. Or simply we do not need to divide it by scalar, and then it can be understood as a unnormalized version of the sample variances and covariances. And yep, this is a estimated version of the estimated version of the, let's say, I will denote it like this. So as you can see from above, there are P variables, explanatory variables. So this can be understood as a sample version of the covariance matrix of the vector X of length P. And let's think of the case where P equals 2. For clarity, it can be easily generalized to a P larger than 2. But for the graphical representation, let's see. So since we have centered all the data points, let's assume that the data points, so it means that there are n data points. So each are the rows. The point of each are the observations. So it is a graphical representation of every row vector of the design matrix X. And they are n data points. And recall that now we're talking about the unsupervised learning case, and what we're interested in is the source of variation. The source of variation. So let's see. You can see that the data points are most variable in the direction of this orange line. And cut to the chase, this is the direction of the first principal component, which explains the most variance of the data points. And why is this important? So we can understand that under these directions of orange line, we can discriminate the respective data points very well. So unlike the first principal component, if we think of the second principal component, so the source of variance is much more smaller than that of the first principal component on the direction of the principal component. So it means that we cannot discriminate between the data points using the, let's say, the coordinate projected onto the second principal component, which is in the direction of this red dotted line. So what we want to do is to find a direction which explains the most variance of the data points. So let's consider, so what we're trying to find is a direction. So direction A, no, let's say alpha. So alpha is a vector of RP. RP, and it means that and we will constrain that its norm, its L2 norm, is 1. In fact, since we're talking about the direction, the norm of the what we say, the direction vector alpha need not to have the norm of size 1. However, in order to keep the meaning of the value of the coordinate respect to the origin point over here, we need to constrain the norm of the direction vector, let's say, it is one of the bases of the orthonormal basis of eigenvectors. Yep. So, yep. Now we are almost done. And let's think of this one. So, we want to find so WTF is an abbreviation of want to find. We want to find a direction vector with constraint on its norm of size 1 such that the variance of and since we did not know the true variance, let's say the estimated variance, so the sample mean, so x alpha to be maximized. So again, in this case, the x refers to the vector of length p. So if we think of the sample version, it can be written as it can be written as 1 over n of, what is it, x alpha transpose and x alpha. And let's see, so if we take one of the row of the matrix X from here, let's say the ith row, so it's like this. And since we've constrained the alpha to the norm of 1, it can be understood as so this is alpha I vector and this is xi. So this inner product can be understood as a scalar projection of the xi vector onto the alpha direction. So it can be understood that this xi transpose alpha can be understood as the coordinate of the projection of the original ith data point onto this alpha direction. So it means that, and there's one more thing to note, which is that since we have centered x column vectors of x into like x, so the sample mean of respective column vectors of matrix X, so here not X tilde, the matrix X, erase this, is 0. So this term can be understood as the variance I'm sorry, since this is a vector, so this is a variance of the alpha transpose x, and this can be re-expressed in terms of like this. Actually, from now on, we're not gonna consider the normalizing constant. It has no effect on the maximization or minimization optimization problem. So what we've got to maximize is the alpha transpose x to the alpha. Yep. With constraint that L2 norm of alpha is 1. And as we learn from the fact, from the, what is it, spectral decomposition or singular value decomposition, this can be rewritten as a factorization of what can I say? V transpose d vector v to the alpha. No. It's both are fine. So for convenience, let's say like this. And okay. And if we write like this way, since it is a positive semi-definite matrix, all the diagonal elements of this matrix D are at least 0. So it is a positive semi-definite matrix at least. And sometimes in order to express that using the fact from the singular value decomposition, we put like square. So I'm going to put square to show that the diagonal elements of this diagonal matrix are at least non-negative. Okay, now we are almost done. So, yep, and we can see, what we can see from here is that it is, so it is like, it's written like this way, F1T alpha, no, the P by 1 vector of like this way. So each V1, V2 until Vp refers to the eigenvectors. So this can be understood as a scalar projection of the vector alpha onto the direction of the first eigenvector. So it's a coordinate on the first eigenvector, and same holds for other p minus 1 elements of these vector v transpose alpha. So what we can say is that if the constraint alpha. Its L2 norm is 1. And I mean, and if we think of the square, if we think of the norm of the V transpose alpha, so it's like this V transpose alpha, and since it is a orthogonal matrix, product of orthogonal matrix, and its transpose, it reduces to alpha transpose alpha, which is 1, which means that its norm is also 1. So let's switch it to the, we can write this form into this way. So C transpose, so we're trying to maximize C transpose D squared C with the constraint that the L2 norm of the L2 norm of the C vector, L2 norm of the C vector is I'm sorry, it's not W, it's 1. Yep. The maximization, the constraint maximization problem reduces to this way. So simply put, C transpose D squared C. I'm going to say the ith diagonal element of D squared as DI. So it can be written as D1 C1 squared plus until dp dp cp squared, and there's a constraint. So what we're trying to maximize is this, the number 1. And there's a constraint that C1 squared plus ... CP squared equals to 1. So again, to emphasize, we actually the constraint need not be the L2 norm equals 1. We are trying to keep this constraint in order to keep the meaning of the coordinate with respect to the origin of the original x1 x2 basis, and if it's smaller than 1, then its coordinate will be contracted. It will go toward the center point 0, and in the opposite case it will stretch out against the center point 0. So anyway, let's think of this constraint optimization case geometrically. So again, for simplicity, let's think of the case of P2 case. So since it is a axis of eigenvectors which are orthogonal, since we were talking about the real symmetric matrix. So this is the V1 and V2. So the constraint of the norm is made like this. And if we think of the contour plot, so let's assume that the D1, so the diagonal element is made in a decreasing order like this. So D1 is the largest, dp, so in this case D2 is the smallest. And if we think of the contour plot of this function. So if we set this to k, then the c then k, then it becomes, so the if d1 is bigger than d2, if we take the reciprocal, or take the root and take the reciprocal, it is smaller than the same thing of d2. So let's say so yep, let's say this is the k of square root of d1, and this is the k of the square root of d2. So if we think of, if 3 is larger than 2, you can easily see that 1 over square root 2 is larger than 1 over square root 3. So this minus k over square d2 and minus k over square root of d1. So if we take the contour plot of the function that we try to maximize, like it will go this way, and like if we reduce it, and it will keep the same shape of this egg-shaped. It can be generalized to the p-dimensional case. So in order to have, so the direction of the highest variance has its maximum compared to the others directions of eigenvectors. In order it to have the same value, the contour plot must be contracted this way. So as we can see, in the direction of the first eigenvector, the variance is maximized at the most fastest speed with just a small move. So in order to a variance to maximize like a certain amount, we only need to move this much in case of the direction of first eigenvector, while we've got to move this much in order to reach the same estimated variance. And if we move this much into the direction of the v1, its variance will get larger than that of the variance of the data points projected onto the v2 eigenvector. So this is the reason why we reduce the dimensionality to the first principal component. Yep. So I think this is the point that I've struggled with, and I hope this geometric explanations better explains why the first, if we project all the data points onto the first principal component axis to the first eigenvector with the highest variance, or the highest diagonal elements, will explain the variance of the original data most. So, and this is the last one. So we've seen that expressed as V D V transpose so so we can think that a V is a orthogonal change of basis matrix. So let's think this way. It's just for a simple understanding, so it may be informal. So if we multiply V transpose on the left and V on the right, it becomes like this. And let's say there's a like no, let's say, oh, I'm sorry. Just a moment, please. I'm sorry. Oh, okay. So, yep. If so like let's say like express a vector in terms of the coordinate with respect to the original basis. So like this alpha transpose alpha, and we can see that so this can be understood as Z transpose, and this can be understood as Z. So in this case, I mean Z to express a same vector of alpha, but expressed in terms of a basis of orthonormal eigenvectors of V. So a vector Z is expressed in terms of V transpose alpha, but in this case we're talking about a vector of p by 1. So if we think of a design matrix, and this is a p by p matrix, so if we think of a design matrix of Z of size n by p, so its first column is a coordinate of the n data points of the first principal component. So it's like this, x and v. So if we think of this, so let's think of we're talking here about the observation vector, which is expressed in the row, and the column vector, or the eigenvectors, like this. Yep. Oh, I think it would be, yep, like this way. Yep. So this is the end of my explanation of the understanding of why the first principal component of the original data point is projected onto that axis provides the most variance among other p minus 1 axes of other eigenvectors. So thank you for listening.